Hello, welcome to another module in this massive open online course. So, we are looking at example problems in DTFT, that is a discrete time Fourier transform. So, let us continue our discussion. Alright, so we are looking at example problems in DTFT. Okay, and so let us start. This is problem number 10 if I remember correctly. Let us start with now this problem deals with the frequency response, not frequency response, actually the difference equation, okay, or impulse response in fact. Impulse response of the given discrete time system. So, we have the difference equation, that is yn equals or yn minus 5 by 6 yn minus 1 equals phi n minus 5 by 6 yn minus 1 plus 1 by 6 yn minus 2, this equals xn, okay, and basically this is the given difference equation, okay. So, this is the discrete time difference equation, something that simulates very similar to a differential equation for the continuous time. So, this is also known as a difference equation. In fact, this is a constant coefficient difference equation. Alright, we have seen how to solve this, or we have seen how to derive the impulse response from the constant coefficient difference equation using the discrete time Fourier transform. Okay. Now, once again, so what we want to find for this problem is what is the impulse response, that is for this system. First, what is the frequency response, which should be very easy to find. What is the frequency response and what is the impulse response? Now, frequency response is simply obtained by taking the DTFT on both sides. Taking the DTFT on both sides, what we have is that DTFT of yn is y omega minus dt 5 by 6 DTFT of yn minus 1 is y omega into e raised to minus j omega, because time shift becomes modulation in frequency, plus 1 over 6 DTFT of y 2 omega, yn minus 2 is y omega e raised to minus j 2 omega. This should be equal to x of omega, which implies, that is h of omega, which implies, just to write it a little bit more clearly, y of omega or y of omega into 1 minus 5 over 6 e power minus j omega plus 1 over 6 e power minus j 2 omega equals x of omega, which implies y of omega over h of x of omega equals h of omega divided by 1 minus 5 over 6 e power minus j omega plus 1 over 6 e raised to minus j 2 omega. And now what I am going to do is I am going to first start by factorizing this, alright, factorizing this, alright, and basically from that the partial fraction expansion, and from that derive the impulse response. So, this is the frequency response h omega, okay. So, this answers the first part of the question. Now, remember this is basically already your frequency response, okay, of the discrete time LTI system. Okay. Now, we have to derive the impulse response. Okay. So, if you take the inverse DTFT of the frequency response, you get the impulse response. So, I have h of omega equals 1 over, and you can easily factorize this you can see is 1 minus 1 over 1 minus 1 over 3 e raised to minus j omega into 1 minus 1 over 2 e raised to minus j omega. Okay. And now, split this into partial fractions, okay, the partial fraction expansion, PF expansion. Okay. Use the partial fraction expansion, and this gives you something very simple. This is 6 times half over 1 minus half e raised to minus j omega minus 1 over 3 1 minus 1 over 3 e raised to minus j omega. Okay. And now, you take the inverse DTFT of each component. Okay. You take the IDFT, and we will use the property basically 1 over 1 minus a e raised to minus j omega has the IDFT a raised to n u n. So, this is the property that we are going to use. Okay. So, this is the, and using this property we can see, taking the IDFT, we have 6 half 1 over 1 minus half e raised to minus j omega is half raised to the power of n u n minus 1 over 3 times 1 over 1 minus 3 e raised to minus j omega is 1 over 3 raised to n u n, which is basically, now if you simplify this will give you well 3 times half raised to the n u n minus 2 times 1 over 3 raised to the power n u n. So, this is your h of n. This is the impulse response of the h of n. Okay. This is the impulse response of the LTI system described by the difference equation. Okay. Described by the given difference equation. Okay. All right. So, now let us proceed to problem number 11, which is the following. All right. So, we consider the LTI system given below. And we have to find what is the frequency response. We have to find a couple of things. What is the frequency response h of omega, what is the impulse response h of omega, and also for this filter what is the three dB frequency. Remember, 3 dB frequency, if you look at a low pass filter, the 3 dB frequency is defined as that point on frequency at which the amplitude is basically 1 over square root 2 that of the maximum. So, basically the power of that point corresponds to half of the maximum, half at the maximum frequency. Alright. So, we require to find also the 3 dB frequency of this filter. Okay. In that sense, so let us start with the impulse response. Now, first let me describe the figure. Now, the figure is very simple, it is a very simple system. So, I have the input x of n. Okay. So, I have x of n is going through the summer, and also x of n which is going through this Bok Z inverse, which we already know corresponds to a delay. Alright. So, this is basically your delay element or delay block, and this is your yn. Okay. And you can see if xn is the input, the output here is xn minus 1, and you are summing xn and xn minus 1. So, the difference equation that describes this is basically yn, it is very simple, equals xn plus xn minus 1. So, this is a difference equation that describes the above system. Okay. So, this is the difference equation that describes the difference equation for the above system. Now, to find impulse response, we set impulse response is basically the response of the system to an impulse. Alright. So, we set xn to be the impulse delta n, and then we find the response or the output of the given LTI system, and that is very simple. So, now to find Hn, set xn equals delta n, and what we get is Hn equals delta n plus delta n minus 1. Now, you can see h of 0 equals delta 0 plus delta 1 equals 1. Similarly, you can see h of 1 equals 1, and you can see that h of n for all other n equals 0 for n not equal to 0 or 1. So, the impulse response is very simple, that is for n equal to 0 h of 0 is 1, for n equal to 1 h of 1 is 1, and for all other n h of n is 0. Okay. So, now the impulse response is basically can be characterized as h of n equals 1, 0 less than equal to n less than or equal to 1, and this is 0 otherwise. The impulse response is 0 otherwise. Okay. And this is basically your impulse response of the system. This is basically impulse response, and now what we also get is x of omega. Now, taking the DTFT to find the frequency response, we have x of omega plus e raised to minus j omega x of omega. This is equal to, well, this will be equal to y of omega, taking the, so this is basically e raised to minus j omega x of omega, that is the DTFT of xn minus 1. Alright, if x of omega is the DTFT of xn. Okay. And on the right hand side, taking the DTFT, that yields y of omega. So, this implies x of omega into 1 plus e raised to minus j omega equals y of omega, implies h of omega, which is y of omega by x of omega, that is equal to 1 plus e raised to minus j omega, which is equal to, you can further simplify this as take e raised to minus j omega over 2 or common, this will be e raised to j omega over 2 plus e raised to minus j omega over 2. But this e raised to j omega by 2 plus e raised to minus j omega by 2 is cosine omega by 2. So, this is simply e raised to, in fact this is 2 cosine omega by 2. So, this is e raised to minus j omega by 2 cosine omega by 2, and this is h of omega. Okay. So, this is your frequency response of the given LTI system. In fact, you can treat it as a filter. In fact, it will be a low pass filter, we will see that. So, this is the frequency response of the given LTI system. Okay. And if you look at the magnitude response, magnitude of h of omega, you can see this is clearly 2 magnitude cosine omega 2. This is basically your magnitude response. The magnitude response is 2 magnitude cosine omega by 2. So, if you draw this, it will look something like this. In fact, it is very interesting, and of course, you can see it is symmetric, it is periodic. Remember, every DTFT has to satisfy the property that it has to be periodic with period 2 pi. So, this is periodic with period equals 2 pi, correct. So, if you look at cosine omega, that will be, it will be periodic with period equals 2 pi. Okay. And now, if you look at this, if you look at this quantity here, I can draw this as follows. So, this is 2 cosine magnitude 2 cosine omega by 2, when omega equals pi, this will be twice. So, at omega equals 0, this is twice cosine 0, which is 2, alright, and when omega equals pi at the ends, alright, it will be 2 magnitude cosine omega pi by 2, but cosine that is 2 magnitude cosine pi by 2, cosine pi by 2 is 0. So, at pi and minus pi as well, it will be 0, and if you look at the frequency response, it will be something like this, which looks basically, and of course, it is periodic with okay, this is periodic with period equals 2 pi. Okay. And this is the peak, you can see magnitude h of omega equals 2. So, this is a plot for magnitude h of omega, and this is omega. Okay. Here it is 2, here it is 0. So, it starts at the maximum at 0 and tapers down, alright, decreases towards minus pi and pi. So, clearly this is a low pass filter, but of course, it is not an ideal low pass filter, because it is not suppressing, that is the attenuation, it is not 0 outside of a cutoff frequency. So, clearly it is not an ideal low pass filter, alright, and therefore, we know that for a non ideal low pass filter, we can characterize the effective bandwidth. One of the ways, one of the metrics to characterize the bandwidth is using the 3 dB frequency. Okay. So, first you can see that this is a non ideal low pass filter, in fact, it is a non ideal discrete time low pass filter. And therefore, what we want to find is what is the 3 dB frequency of this non ideal low pass filter, and that can be magnitude h of omega. And if you look at the max of this occurs at h of 0, this occurs at 0, which is 2 magnitude cosine 0, which is equal to 2. Now, the 3 dB frequency omega naught, so let us call this omega naught. Now, this will have to be such that magnitude h of omega naught is 1 over square root of 2 times maximum of the magnitude of h of omega, which is 1 over square root of 2 times 2, which is square root of 2. Remember, at the 3 dB frequency, the amplitude has to be 1 over square root of 2 times that of the maximum amplitude, alright, times that of the maximum gain, that is the amplitude gain of the low pass filter. And now this is very simple. So, we have 2, assuming omega greater than 0, for omega greater than 0, for omega less than 0 it is symmetric, 2 cosine omega by 2 equals square root of 2 implies, or in fact this is omega naught, implies cosine omega naught by 2 equals 1 over square root of 2, implies omega naught 2 is now cosine inverse 1 over square root of 2, which is pi by 4, implies the 3 dB frequency omega naught equals pi by 2, very simple. Okay. So, the 3 dB frequency omega naught equals to pi by 2. So, the 3 dB frequency is pi by 2, and if you look at this, you can indicate the 3 dB frequency over here. If you look at pi by 2, what this is saying is that if you look at pi by 2, this will be 1 over square root of 2, and therefore, this will be your 3 dB frequency. And 3 you can also say that the 3 dB bandwidth, okay, the 3 dB bandwidth of the filter. You can also say for this non-ideal low pass filter, the 3 dB bandwidth is basically pi over 2. Okay, all right. So, that completes the analysis of this problem. Let us now move on to the next problem, which is also very interesting. Let us look at how to derive a high pass filter from a low pass filter. Okay, so, this is my problem number 12, and we will see an interesting technique to derive a high pass filter given a low pass filter, a discrete time high pass filter. Okay. So, let Hn be the impulse response of ideal LPF low pass filter, and the cutoff equals omega c. Remember, every ideal low pass filter will have a cutoff frequency. Now, what we want to do is we want to consider minus 1 to the power of n Hn. Let us denote this by H tilde n, and we want to demonstrate that this is in fact a high pass filter. So, our question is, what is H tilde of omega? And in fact, if since Hn is ideal low pass filter, if you look at for instance, if you look at H of omega, that will look something like this, and remember it is all periodic with respect to pi or 2 pi. So, this will be something like this. So, it is not necessarily according to scale. So, this is pi, this is minus pi, and this is omega c, the cutoff, and minus omega c, or let us denote this by omega c, minus omega c, and this is omega c, and this is your magnitude h of omega, and this is omega. Okay. And this is basically your cutoff frequency. Okay, this is your cutoff frequency. Let us call this omega c. Okay. Now, what is the cutoff frequency in this case? Minus, so h tilde n equals minus 1 n h n. If you look at h tilde n equals minus 1 n h n. Now, you can write this minus 1 is e raised to j pi, alright. So, minus 1 raised to n is e raised to j pi n, and then you will observe something interesting. So, this is e raised to j pi n times h n, which is e raised to j pi n times h n, and you can see this is modulation in time. Okay, this is of the form e raised to j omega naught n, or this is of the form e raised to. So, we use the modulation property. Okay, so, the modulation property states that, remember, you can recall, if h of n has DTFT h of omega, then e raised to j omega naught n has DTFT e raised to j omega naught n has DTFT h of omega minus omega naught. This is your modulation property. Okay. So, which means e raised to j pi n has DTFT equals h of omega minus omega naught. So, here omega naught equals pi. So, DTFT will be h of omega minus pi, okay, and that is your h tilde of omega. So, h tilde of omega corresponding to minus 1 raised to n h n. So, h tilde omega is h of omega minus pi, which is basically what you are doing is you are taking the low pass filter response and you are shifting it by pi, and remember it is periodic. Okay. So, the shifted version, that is h tilde of omega, will also be periodic, in fact with period 2 pi again. Okay. So, simply shifting does not either induce or destroy periodicity, alright. So, the original signal is periodic, the shifted signal will also be periodic, in fact the period will also be the same. Okay. So, this is the shifted LPF, and once you shift the LPF, remember with cutoff frequency omega c, and it is very easy to derive that, that is going to look something like this. So, you take the original LPF, you shift it to pi, so it will be now centered around pi, and so this is pi, and this is 2 pi. At 2 pi it will be 0. So, at 2 pi it will be 0, because originally what is at pi will come to 2 pi, alright. You are shifting it, or originally what is at 2 pi will come to pi, what is 3 pi will come to 2 pi, which is also anyway 0. So, and rest is, it is periodic with omega. Okay. So, this is pi, so this is minus pi, and you will also have something that is basically looks like this, and now this point, if you realize, this basically shifted by pi. So, originally so this is omega c, when you delay it by pi, this will become omega c minus pi, and this will become pi minus omega c. So, this point will become, in fact I am sorry, this point will become, so this is basically pi minus omega c, and this is omega c minus pi, or minus pi plus omega c. So, now you can clearly see gain is 0. If you look at magnitude h tilde omega at 0, this is equal to 0, and gain at pi is equal to the at pi gain is equal to 1. So, what you can see at 0, earlier at 0 it had the maximum gain, at pi the gain was 0, cutoff was omega c, alright. And now in fact let me just write it as capital omega c. And now what is happening, because of this shift by pi, alright, the maximum gain is now at pi, alright. So, maximum gain is unity, and in fact at 0, alright, the gain is 0, alright. So, this is now a high pass filter, okay. So, using this modulation minus 1 raised to n Hn, we have converted a low pass filter into a high pass filter, into an equivalent high pass filter with a cutoff frequency pi minus omega c, okay. So, that is now the cutoff frequency, okay. So, the cutoff frequency of this will be pi minus omega c. And this is a high pass filter. So, H tilde n you can see we will have the DTFT. So, we have minus 1 to the power n H tilde Hn equals H tilde n, which is the DTFT, H tilde omega, which is H of omega minus pi, and this is basically, therefore, this is a, now this is, now Hn is a low pass filter and H tilde n, this is a equivalent high pass filter, in fact an ideal high pass filter, ideal HPF, this is ideal HPF, cutoff equals pi minus omega c, okay. So, that is what we are able to, that is what we are able to show, alright. So, that is a very interesting problem, and it shows an interesting trick of how to derive an equivalent high pass filter, correct, once you have a ideal low pass filter, and for that matter it works also for non ideal, that is corresponding to a non ideal low pass filter, one will derive a non ideal high pass filter, alright. So, let us stop here and we will continue with other problems in the subsequent modules. Thank you very much.